There's a planet that has been breaking the law for 100 years, out in plain sight, where anyone with a good enough telescope could sit and watch it do the crime. And for the longest time, nobody alive could work out how it was getting away with it. The planet is Mercury, the little one, the one that runs closest into the sun and quickest round it, whipping through its whole year while the rest of us are barely out of the gate. And the law it keeps breaking is the oldest, surest law of the heavens we ever had, Newton's law. The one that says a planet, left alone, traces the same clean loop around the sun, over and over, coming back every single time to exactly the same nearest point, forever, without slippage, till the end of the world. Mercury won't do it. Its loop slips. Every time round, the point where it swings in closest creeps on a hair further than it has any right to, so that over the long, slow grind of the years, the whole orbit turns in place, like the hand of a great clock that nobody wound. A tiny thing, a ridiculous, impossible thing, and it survived every patch the finest minds on Earth could throw at it. So, in the end, they did the only thing left to do. They invented a whole hidden planet to blame it on, gave it a name out of the old fire myths, and sent telescopes hunting for it, close in against the glare, for the better part of a lifetime. They never found it. And I'll tell you why they never found it, because there was nothing there to find. The thing tugging Mercury's loop out of true was not a planet hiding in the sun's light. It was the shape of space itself. And not one soul on Earth was ready to be told that.
Not one. And the reason I've got a grin on that I can't quite put away is that you've walked in and set down, in your own words, the exact scene where our whole story tonight begins, and the exact wound it heals. Hold that wobble. Don't let go of it, the little planet that will not close its loop. Because by the end of the night, I'm going to hand it back to you. Solved. And the solving of it is one of 3 great blows that turned a beautiful equation into a true description of the world.
A beautiful equation. That's where you left me last time, and rather cruelly, I thought. You gave me Einstein's equation, matter on the one side, the shape of space-time on the other, each one telling the other what to do, round and round forever. And then, right at the door, you dropped a name on me like a coin down a well and sent me up the stairs. You said a soldier solved it.
I did. And I mean to earn that tonight, because it's one of the strangest true stories in all of physics, and the strangeness of it matters. So cast your mind back to the equation as I handed it to you. What did I tell you about how hard it was to solve?
You told me it was a monster, that it bit its own tail, so tangled up with itself that even Einstein, who'd built the thing, didn't believe you could ever solve it cleanly, only creep up on it with rough guesses, you said. Approximations, never the exact answer.
That was the settled wisdom, from the man who wrote it, no less. This equation is so knotted, so wound round on itself, that an exact solution, a clean, closed, perfect answer for the shape of space-time around anything real, was thought to be a dream. You'd get near it the way you creep up on a shy animal, with careful approximations, and that would have to do. And then, within a few short months of Einstein setting the equation loose on the world,
somebody just walked up and solved it.
Somebody just walked up and solved it. Clean, exact, perfect. The complete shape of curved space-time around a single round mass, dropped out whole. No approximation anywhere in it, every corner of it nailed down.
Now, hang on. You keep leaning on that word exact, like it's the whole prize. Why does exact matter so much? If the approximation's already got you close, who cares whether the answer's perfect or merely very, very good?
A fair push, and here's the answer. An approximation tells you the truth in the gentle places, far from the mass, where the warp is shallow, where nothing much is happening. But it's precisely in the fierce places, close in, deep in the steep part of the warp, that an approximation starts to fray and lie. And the fierce places are where the whole drama of tonight lives. The innermost planet, the starlight grazing the sun's edge, and one thing far worse waiting at the very end. An exact solution doesn't fray. It holds all the way in, right down to where the numbers start to scream. That's why it's the prize.
All right, exact means it holds where it matters. So, who held it? Who's the soldier?
A serious man, no boy. A real career behind him, who, when the great grinding war came, went off to serve. And not to a desk either. He went up to the front, where the guns were, and spent his days doing the grim arithmetic of shells and their arcs. And in whatever scraps of night he could steal, in the mud and the cold and the noise of it, he took Einstein's brand new, supposedly unsolvable equation and solved it.
You're not serious.
Entirely serious. Worked the whole thing through by hand, out there at the front, and found the exact shape of space-time around a star. And then he did the most extraordinary thing of the lot. He put it in an envelope and posted it back to Einstein. From the trench.
He mailed it to Einstein. From a war. Dear Professor, hope this finds you well. I appear to have solved your impossible equation between the shelling. Do let me know what you think.
Very nearly the tone of it, by all accounts. And Einstein, who hadn't believed it could be done at all, reads this thing that's arrived from the front and is so struck by it that he takes it up himself, in person, and lays it before the learned world on the soldier's behalf. Says, in effect, I never expected the exact answer to come so simply, and here it is. The name on that envelope was Schwarzschild, and it's his name we've hung on the thing ever since. The Schwarzschild geometry, the Schwarzschild solution. The first exact map of curved space-time ever drawn.
How do you even do that? Sit in a trench, with shells coming in, and hold a piece of mathematics that hard in your head? I lose my train of thought if someone slams a door.
I've wondered the same thing my whole life, and I've no good answer for you. Only that some minds, put in the worst place a person can be, reach for the one thing that's still clean and orderly and entirely theirs, and hold on to it like a rope over a flood. The equation may have been the calmest room he had left to sit in.
Schwarzschild. And what became of him? A man who does a thing like that. From a trench, no less. I want to hear he came home to a hero's welcome and a good, long life.
He didn't come home. That's the ache in the middle of it. He fell ill out there. Not from a shell, from a sickness he took at the front. And he was gone within months of doing perhaps the finest single piece of work of his life. He never saw where it led. He drew the first true map of the space around a star, and he didn't live long enough to watch the whole cosmos come pouring out of it. So when we say his name tonight, say it kindly. He earned it in the worst place a person can earn anything.
I will. Genuinely, that's a lot to sit with. He solved the shape of the universe in a trench and then died of it. All right, tell me what he actually found. This map. What is the Schwarzschild geometry a map of?
Of the emptiness around a star, or around anything round and heavy. A planet, the sun, a marble if you like. It doesn't care how grand the mass is. Take one lump of matter, round, sitting all alone in the dark, nothing else in the whole universe to complicate it. Now ask Einstein's equation the one question it exists to answer. Given that mass sitting there, what shape does it force on the space-time all around it? And Schwarzschild's answer is the exact, complete shape. Point by point, everywhere outside the mass, out to the ends of the empty dark. Here is exactly how curved space-time is at this distance, and at this one, and at this. A full map of the warp.
And I'm going to reach, straight away, for the very picture you keep warning me of. The heavy ball on the rubber sheet, sagging a dent into it. The little marbles rolling round the dent. Because that's the picture everyone's got in their head. Is that the map or isn't it?
It's the picture everyone's got, and I'll let you keep a corner of it if you promise to hold it honestly, because it lies in two ways, and both of the lies matter. The first lie, it shows you a sheet, a flat, rubbery surface, bending down into some third dimension underneath it. But there is no underneath.
No underneath, so what's it bending into?
Nothing. It isn't bending into anything at all. Remember the ant, the little ant on the ball, who could prove its whole world was curved without ever once leaving the surface, just by measuring triangles that came out wrong. Space-time is curved like that, from the inside. It doesn't sag down into a lower room. There is no lower room. The curving is a thing you measure from within, with rulers and clocks, and it needs no outside to sag into.
Fine, no outside the ant, I've got it. And the second lie?
The second lie is the deep one, the one this whole season has been quietly built to correct. The rubber sheet shows you space bending, only space, a dent in a floor, but near an ordinary star, near the sun, near the earth, near anything you'll ever stand on or fall toward. The thing doing nearly all the work isn't the bending of space at all. It's the bending of time.
The bending of time. You keep coming back to that, and I keep almost having it and then losing it. Say it once more, slowly, the way you'd say it to someone half asleep.
Then here it is, slowly. Down near a mass, time runs slow. Not as a trick of the clocks, really truly slow. A clock down low, deep in the dip near the mass, ticks off its seconds more sluggishly than a clock up high where the mass's grip is fainter. We felt this coming as far back as the elevator, the clock at the floor of the accelerating rocket lagging the clock at its ceiling. Schwarzschild's map now hands you the exact amount at every single distance from the star.
And that slowness of time, that's the thing that makes me fall?
That's the thing that makes you fall. When you drop an apple, when you yourself step off a ledge, what you're really doing is sliding toward where time runs slowest. That leaning toward slow time is the falling. It's very nearly the whole of gravity near an ordinary star. The dip in the sheet you can see with your eyes, that's the small part. The dip in time you can't see, that's the mountain.
So the marble doesn't roll into the dent because the sheet's tilted under it. The marble, the apple, me, the whole planet, falls because time itself is deeper on one side than the other, and everything drifts toward the deep end.
Everything drifts toward the deep end, and it drifts along the only honest path there is, the straightest path it can take through that warped shape. That's the whole of the machinery. No hand reaching across space to grab you, no rope, no force in the old sense. A planet doesn't orbit because something's yanking it round in a circle. It orbits because a loop through the warp is the straightest path it's got. It's falling and forever missing. Just a mass, warping the space-time around it, mostly the time of it, and everything else falling along the straightest line still available. Schwarzschild's map is the thing that tells every falling apple and every passing beam of light exactly where that straightest line runs.
All right, that's the map. It's honest, it's from a trench, it's mostly about time, and it's exact. But a map's only worth the paper it's printed on if it tells you something you didn't already know. Newton had a map too. His was a force reaching across the dark, and his map was very, very good. It flew every planet round the sun for 200 years and never once put a foot wrong. So what does Schwarzschild's map tell you that Newton's doesn't? Where do the two of them actually disagree?
Now you've asked the right question, and it's the question that made all the difference in the world. For nearly everything, everywhere, the two maps agree so closely you could never tell them apart. Drop an apple, fly a rocket to another planet, run the whole clockwork of the heavens. Newton's answer and Schwarzschild's answer sit right on top of one another, near enough as makes no difference.
So Newton wasn't wrong.
Newton wasn't wrong. Newton is a magnificent approximation. Say that plainly and keep saying it, because the story here isn't Newton being a fool. It's Newton being very slightly, very deeply, not quite right, in a way that took 2 centuries and a warp map to catch. In a very few places, where the mass is great and you get in close, where the warp turns steep, the 2 maps peel apart by the thinnest sliver. And that sliver is everything.
Why is a sliver everything? If they agree almost perfectly almost everywhere, who on earth cares about a sliver?
Because a sliver is testable. If Einstein's map is right and Newton's is only nearly right, then somewhere out there must be a place where reality follows the new map and not the old one. A place where you can catch Newton being not quite right and catch Einstein being exactly right, out loud, where anyone can check. And I'll bet you already know where the first such place is. You've been dangling it since your very first breath tonight.
Say it's Mercury. Please say it's Mercury.
It's Mercury, the law-breaking planet. Closest into the sun, deepest into the warp, whipping round fastest through the steepest part of the whole thing. Of all the worlds, exactly the one where a little disagreement between the maps gets the best chance to show itself. So let me give you the crime in full now, properly. Newton's map says a lone planet round the sun traces an ellipse, a stretched loop, and, this is the heart of it, the same ellipse every time. It closes. The point of closest approach, call it the near point, sits in one fixed spot, and the planet returns to that exact spot, loop after loop after loop, and the whole figure never budges. A closed, faithful, eternal loop.
And Mercury's loop doesn't close. It creeps. The near point walks around.
It walks. Ever so slowly, but it walks, the whole ellipse turning bodily on the spot, so the near point traces out its own vast, slow circle across the ages. The loop rotating like the hand of that unwound clock you gave me at the start.
And the astronomers must have tried the obvious thing first, the other planets. Everything else out there tugging on it.
The first and most sensible thing. Mercury isn't alone. Every other planet is pulling on it, and Newton's math handles those pulls beautifully. So they added up every last tug from every other world, turned the crank, and out came a prediction for how much Mercury's loop ought to turn from all that hauling.
And it turned by more.
It turned by more. The tugs of the other planets explain nearly all of the creep, almost the whole of it, but not quite. A sliver was left over. A small, stubborn, extra amount of turning that all the tugging in the solar system could not pay for. Tiny, but there, year after year, patient and unarguable, and it would not go away.
And that leftover sliver is the loose thread. That's the bit that quietly breaks Newton.
That's the bit, and you have to feel how badly it itched. Here is Newton's gravity, the most successful idea in the history of science, never once caught wrong in 200 years. And here's this absurd little leftover wobble on the innermost planet that it simply cannot cover. So what do? You reach for the thing that had worked gloriously the last time.
Which was?
Not long before, someone had noticed a different planet misbehaving out at the far cold edge of the system. And rather than doubt Newton, they'd said, there must be an unseen world further out still, tugging on it. They worked out where that unseen world would have to sit, pointed a telescope at the spot, and there it was. A brand new planet, found on the tip of a pencil before any eye had seen it. The single greatest triumph Newton's gravity ever had.
So of course they ran the same play again. Mercury's misbehaving? There must be another hidden planet, only this time an inside one, tucked in tight between Mercury and the Sun, lost in the glare, doing the tugging.
The very same play, and it was a good bet, not a stupid one. It had just paid off spectacularly at the other end of the system. So they worked out where this inner world would have to be. They even gave it a name in advance, out of the old myths, the god of the forge and the fire, which is a fine name for a world huddled that close to the furnace. And they went hunting.
For the fire planet. And?
For the fire planet. Every eclipse, every time anything crossed the sun's face, every chance to peer in close against that blinding edge, someone was looking for the little world that would save Newton's law. For years, decades.
And it was never there.
It was never there. No planet, no moonlit, no ring of dust. Nothing tucked in close enough and heavy enough to do the job. The sky was empty in exactly the spot the theory needed it full. And so it sat, the splinter under the fingernail of physics, unresolved for the better part of a lifetime, until a soldier's exact map came home from a war.
And you're going to tell me it just falls out. The wobble. You feed the sun's mass into Schwarzschild's map, you ask how Mercury's straightest path runs through the warp, and
out it comes, the whole of it. You take the exact shape of space-time around the sun, Schwarzschild's shape, not Newton's, and you ask the only question the theory ever asks. What is the straightest possible path for a small planet through this warp? And the answer is a loop that doesn't quite close. On Einstein's map, the near point is supposed to creep. The ellipse is supposed to turn. It isn't a flaw, it isn't a leftover, it isn't a missing planet. It's simply what the straightest path does when the space-time is shaped this way instead of the way Newton imagined.
And the amount it creeps.
The amount it creeps comes straight out of the map, and it matches the stubborn leftover wobble. Right on the nose. Not roughly, not near enough. The very size of the thing Newton couldn't cover, Einstein's geometry pays in full. Exact change. No hidden planet required.
So there was never a fire planet at all.
There was never a fire planet. There was only ever the shape of space-time being very slightly different, close into the sun, from anything Newton had dreamed. Steep enough in there that Mercury's loop can't hold its line. Every other planet rides too far out, in the gentle part of the warp, for the difference to show. Their loops close, near enough, and Newton keeps them beautifully to this day. But Mercury, running closest, deepest, fastest, feels the true shape of the thing. And it has been quietly announcing, for 100 years, in a wobble too small to be anything but a message, that Newton's universe is the wrong shape.
That gives me a real shiver, and I want to say why. It's not that Einstein predicted something wild and new that nobody had ever seen, it's the opposite. The thing was already there. It had been sitting in the data for generations, staring everyone in the face, breaking the sacred law right out in the open. And it took the new map to look at that old, stale, embarrassing little wobble and say, that isn't a mistake, and it isn't a missing planet. That's the shape of the world, and you've been reading it wrong the whole time.
That's the whole of it, and it is the first of the 3 great blows. And notice what kind of triumph it is. A quiet one. A theory tidying up an old, known, annoying fact that everyone had already half given up on. That doesn't make headlines. That doesn't wake a man up famous. For that you need the second blow, the one where the theory sticks its neck all the way out, makes a bet about something nobody has ever measured, and lets the whole world watch to see whether it hangs.
Then give me the second blow. What's the bet?
Light. The bet is about light. Think back all the way to the accelerating elevator, the box. What did we decide gravity does to a passing beam of light?
It bends it. We fired a beam across the accelerating rocket and watched it land low because the floor rushed up to meet it. And since the box can't tell acceleration from gravity, a beam crossing a room in real gravity has to bend the very same way. Light falls. Even light, with no weight to it at all, falls.
Light falls. So already, before any exact map, before Schwarzschild, we knew starlight skimming past the sun, sliding through the steep part of the warp, ought to bend. A ray from some far-off star, grazing the sun's edge on its way to us, should get its path nudged, so the star it came from appears shoved a hair to one side of where it truly sits. That much we had. But here's the trap, and it's a lovely one. Newton can play this game too.
Newton? How does Newton bend light? Newton's gravity is a pull on things with mass. Light has no mass. There's nothing for the pull to get hold of.
But pretend, just for a moment, the way people once genuinely did, that light is a hail of tiny bullets, little corpuscles streaming past the sun. If you insist on that old picture, then even in Newton's world, the sun's pull would tug those bullets as they pass and bend their path by some amount. A definite amount. You can work it right out. So now there are two numbers on the table. Newton's number, the bend you'd get treating light as falling bullets, and Einstein's number from the true curved space-time map. And here's the whole knife edge of the night. They are not the same number.
They're different. By how much?
Einstein's is twice Newton's, exactly double. The full curved space-time map bends the starlight by precisely 2 times the amount the old falling bullet picture gives. And that factor of 2, that plain, clean doubling, is the sharpest test in the whole story.
Why is it the sharpest? Both of them say light bends. Surely the win is just seeing it bend at all.
That's the trap, and you've walked right into it, which is perfect. If all you ask is, does starlight bend past the sun, and the answer comes back yes, you've learned nothing whatever, because both theories said yes. Newton said yes, Einstein said yes. Seeing it bend settles nothing at all. The only question that separates them is by how much. Einstein says twice. So the whole test, the entire thing the world would hold its breath on, isn't the bending, it's the doubling. Catch the doubling, and you've caught Einstein being right exactly where Newton is wrong.
But hold on, why twice? Where does the extra bend even come from? If Newton and Einstein agree that light falls, why on earth doesn't it fall by the same amount?
This is my favorite thing in the whole episode, so let me lay it out with both hands. Remember what I told you a while back, that near an ordinary star, it's the bending of time that does nearly all the work, and the bending of space is only a small thing. For a slow apple, for a slow planet, that's true. The apple ambles along, and it's the slope of time it mostly feels. The actual curving of space barely gets a vote. But light is not slow.
Light is the fastest thing there is.
The fastest thing there is. And when a thing moves that fast, the curving of space stops being a small correction and stands right up to its full height. It gets an equal vote. So light feels both. It feels the bending of time, the same thing the apple feels, the part that stands in for Newton's old pull. And on top of that, it feels the bending of space, which the slow apple could afford to ignore, and the racing light cannot.
So the time part gives one helping of bend.
The time part of the warp gives you one helping of bend, and that one helping is, near enough, Newton's number, the falling bullet amount. And then the space part of the warp, the part the slow apple ignored but the light can't, adds a second helping, the very same size as the first. One from time, one from space. Add them together and you've doubled it. That is where the factor of 2 lives.
So the 2 isn't a fudge. The 2 is 2 because there are 2 things bending the light. Time and space, one helping each.
One helping each. And Newton, with only his pull, only ever gets you the time half. He's missing the whole of space, because in Newton's world, space is just the empty stage, flat and inert and the same everywhere, a thing that could never bend because there was nothing to it to do the bending. That factor of 2 is the sky's way of saying, no, the stage bends too. It's the fingerprint of space itself being curved, the very thing the rubber sheet was always straining to show you. Finally standing up to be counted, because only something as fast as light leans on it hard enough to make it show.
That's beautiful. All right, you've got the bet. Starlight past the sun bends by twice Newton's amount. Now, how in the world do you test it? What do you actually have to do?
You'd have to catch a star whose light just skims the very edge of the sun on its way to us, and measure whether it's been shoved aside, and by exactly how much. So, go on, tell me the problem with that.
The problem is, it's mad. You can't see a star anywhere near the sun. The sun's the most blinding thing in the entire sky. Any star sitting right up against its edge is drowned dead in the glare. You'd never pick it out. It'd be like trying to spot a single candle held up beside a searchlight.
It's exactly like that. And that's the impossibility that stood in the way. Until you remember there's one moment, and only one, when the searchlight goes out.
The eclipse! When the moon slides dead in front of the sun and blocks it clean out. The sky goes dark in the middle of the day, and the stars come out. The stars right next to the sun come out because the glare's been switched off.
The one moment the searchlight goes dark. For those few minutes of a total eclipse, the moon caps the sun exactly. Day drops to a deep, unearthly twilight, and the stars, crowded close around the sun's hidden edge, blink into view. The very starlight that has come grazing past the great mass on its way to us. So here's the plan, and it's a thing of patience and nerve. You wait for a total eclipse. You carry your instruments to wherever on Earth the moon's shadow is going to fall, and you camp there, and you pray for a clear sky.
And you can't exactly order the weather. All that effort, hauling delicate glass to the far side of the world for a few minutes of darkness, and a single cloud in the wrong place ruins the whole thing.
A single cloud ruins the whole thing. That's the nerve of it. You get one throw of the dice, a handful of minutes, no second try for years. But suppose the sky is kind. In those few dark minutes, you photograph the patch of stars crowded around the blacked-out sun. You catch their positions. Then you wait, months, until that same patch of sky rides high in the ordinary night, the sun long gone off to the far side of the year. And you photograph the very same stars again, this time with no sun anywhere near them, sitting in their true, undisturbed places. And then you lay the two pictures down side by side.
And if Einstein's right, the stars nearest the sun's edge will have shifted between the two. In the eclipse picture, they'll be nudged outward, shoved away from the edge, compared to where they really sit in the calm night picture, because their light got bent coming past.
Nudged outward, every one of them, by an amount that grows the closer the star sits to the edge. Most shifted right at the rim, less the further out you look. And not merely shifted by the double amount. That's the needle the whole world was threaded on. Not, did they move by Newton's amount or by twice Newton's, the half or the full.
And when the plates were compared, and the little shifts read off the crowded stars around that black sun,
they'd moved the full amount, twice Newton. Einstein's number, not the old falling bullet number. The doubling was right there in the sky, written in the shoved-aside starlight. The stage bends too, and the stars had said so.
And that's the one that made him famous.
That's the one. When the news got out that starlight itself had been caught bending by the new amount, that the sky had sided with Einstein against 200 years of Newton, it didn't stay in the journals. It crossed every ocean by morning. It ran across the front of every paper in the world. A man who the day before was known to a few hundred physicists woke up the most famous person alive. The one who had weighed light and bent starlight and caught Newton being not quite right in the one place it could be caught, overnight, from a wobble in a photograph.
From a wobble in a photograph. There's a lovely rhyme in that, isn't there? The first blow was a wobble in a planet that nobody could explain, and the second was a wobble in a star that Einstein explained before anyone even measured it. One old wobble saved, one new wobble called in advance, and then caught.
And that rhyme is the whole difference between a good theory and a true one. The first blow showed it could clean up the past. The second showed it could call the future, stick its neck out on a number nobody yet had, name the doubling ahead of time, and be proven right by the sky. That's the one that made him immortal. But there's a third blow, and though it made the least noise of the three, in some ways it goes the deepest. Because it's the one we've been quietly promising you since the second night of this whole course.
The clocks, the redshift, the thing with the elevator and the light losing its pitch.
The redshift. Let me build it back up. It's been a while. Down near a mass, time runs slow. We've said it 3 times tonight. We said it with the elevator long ago. Now think hard about what light actually is. A wave. A thing that beats, that ticks, crest, 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 at some steady rate. So a beam of light is, in its own quiet way, a clock. Its colour is its ticking rate. Fast beating runs toward the blue, slow beating runs toward the red.
So if I make a beam of light down low, deep in the warp where time runs slow, and then it climbs up out of the mass toward me.
Then it was born to the slow beat of the deep place. It ticks at the sluggish rate of down there, because down there is where its clock got set. And as it climbs up out of the mass, up out of the dip in time, toward where clocks run quicker, it can't speed its own beating up to match the new neighborhood. It keeps the slow beat it was born with.
So to me, up high, waiting for it.
To you, up high, the light arrives beating slower than any light you'd make with your own hands. And slower beat means redder. The light's been reddened, not by moving away from you, not by any speed at all, but purely by climbing up out of slow time into fast. Light climbing out of a gravity well loses its pitch, reddens on the way up, exactly as we swore it would back in the elevator with no map at all in our hands. And now Schwarzschild's map gives you the precise reddening at every height.
And I'm guessing this one was the very devil to measure. Bending starlight. At least you've got the whole sun to do the bending, and a total eclipse to see it by. But the reddening of a beam crawling up out of a star, that sounds fantastically tiny.
Fantastically tiny. So tiny, it was the last of the 3 to be pinned down for certain, and it took a long time and enormous care to do it. But pinned down it was. Light climbing up out of great masses was caught, in the end, arriving reddened by just the amount the map foretold. Not a whisker more, not a whisker less.
And I'd guess we've got better at it since.
Far better. In ways I'll not spoil, we later learned to measure it so finely we can catch time running slow over the mere height of a building, over the height of a person, near enough. Your head, held up higher, sits in faster time than your feet do. It's true. It's measured. Your head is very slightly older than it would be if you'd spent your whole life lying down. And all of it started here, with this third quiet blow. Light comes up out of a gravity well, tired and reddened, exactly on schedule.
So there they are, 3 of them. The old wobble Newton couldn't pay for, paid. The starlight bending by the doubled amount, caught in an eclipse. And the light climbing up out of the deep, reddening as it comes, measured. 3 completely different things in 3 completely different corners of the sky, and one map from one trench gets all 3 exactly right.
All 3. And that's the moment a beautiful equation stops being a beautiful equation and becomes the truth about the world. One idea that space-time is a shape and things fall along the straightest path through it, reaching out and correctly telling you three separate things that Newton either got wrong or couldn't touch at all. It's one of the great winning streaks in the history of thought.
So this is your moment to be smug, then. 3 for 3. The whole thing gift-wrapped. Newton dethroned. Everyone home for tea.
Newton dethroned. Gently, respectfully, still perfectly good for flying you to the moon, but dethroned as the deepest word. The deepest word is geometry now, and yes, it would be my moment to be smug. If the map were only ever kind. But I haven't told you the whole of what came home in that soldier's envelope, because the same map, the same clean, exact, gorgeous map of the space around a star, has a place in it where the numbers stop making sense, where they go mad.
Go mad? How? A minute ago it was handing you exact right answers about Mercury and starlight and reddening. Now it goes mad?
Follow the map inward and watch. Start far out from the star, out in the gentle country, and walk in toward the mass. Closer, closer, and watch the warp steepen as you go. Time runs a little slower, then slower still, the deeper in you get. All smooth, all sensible. And then, at one particular distance from the center, one specific radius, a ring drawn round the mass at a certain closeness, the map breaks.
Breaks how?
The arithmetic screams. According to the numbers, right there on that ring, time doesn't merely run slow. It stops, grinds to a dead standstill, and distances swell up toward infinity, the tidy geometry tearing itself to rags. One clean radius, where the whole beautiful shape stops meaning anything at all.
Time stops. That can't be a real place. That has to be the map going wrong, not the world.
And that is exactly what Einstein thought. What very nearly everyone thought for a long, long while. Because look at where this mad radius actually falls, for anything real. For the sun, that ring, the distance where the numbers go mad, sits a mere few miles out from the very center of it.
A few miles. Out of a sun that's, what, hundreds of thousands of miles across?
Hundreds of thousands of miles across. So the mad ring, for the sun, is buried unthinkably deep, miles from the center, drowned under the whole enormous weight of blazing gas. And remember what the map is a map of. The empty space outside the mass. Down there, miles from the center, you're not in empty space at all. You're buried in the very heart of the star, where the map was never meant to apply. So the mad ring is drowned, tucked away in a place you could never reach, in a region the map doesn't even claim to describe. A blemish that never once shows its face.
So you just shrug it off. The map screams at one radius, but that radius is always buried harmlessly deep inside the star where it doesn't count. So who cares?
Who cares? That was the verdict. A ghost. A mathematical phantom, an artifact of the arithmetic, a place the equations misbehave, but that no real object could ever expose. Because to expose it, to lay that mad ring bare out in the empty space where the map does apply, you'd have to do something absurd.
Which is?
Take the whole star, all of that mass, and crush it down smaller than the mad radius itself. Squeeze the entire sun into a ball just a few miles across. And nothing, surely, nothing in all of creation is that dense. Nothing crushes itself down inside its own mad ring. So the ring stays buried forever, and the ghost stays a ghost, and everyone sleeps soundly. That was the reasoning. Einstein went to his grave, very near enough, sure that the place where his own solution broke was a phantom the real universe would simply never permit.
But you said that with a look on your face. Nothing's that dense. Surely? You don't lean on the word surely like that unless it's about to give way under you.
I don't, do I? Sit with the shape of the assumption for a moment. The whole comfort of it, The entire reason the mad ring gets to stay a harmless ghost hangs on one single word. Surely. Surely nothing's that dense. Surely nothing ever gets crushed that small. The ghost is only a ghost, for as long as that one word holds.
And you're about to tell me the word doesn't hold.
I'm about to leave you wondering, which is worse? Here's the loose thread I'm hanging over your bed tonight, the way you hung Mercury's wobble over mine all these weeks. What if it doesn't hold? What if, somewhere out in the dark, something really does get squeezed that small? The whole of a great mass crushed down inside its own mad ring, so the ring is no longer buried in the heart of a star, but laid bare out in the empty space where the map does apply. Out where you could actually go.
Then the ghost stops being a ghost.
Then the ghost stops being a ghost and becomes a place. A real place with a real edge drawn on the true shape of the world. A ring you could fall across. And once you'd fallen across it, the map is telling you time stops there, distances tear, the whole geometry goes mad.
An edge you could fall through going in and never climb back out of.
Never. That's the shape of the thing waiting under all tonight's triumph. And Einstein, one of the greatest minds our kind has ever produced, the man who built the whole cathedral this map hangs in, was sure it was impossible. Sure it was a ghost. On this one thing, I've come to believe, the universe was quietly waiting to prove him wrong. The mad radius isn't a flaw in the map. It's a warning printed right on it. A place marked here the world stops making the kind of sense you're used to.
And the only question left is whether anything's heavy enough, and stubborn enough, and squeezed enough to actually go there.
That's the only question left. And I already know from your face that you've guessed the answer.
I have. From the gentle way you've set it all down, the answer's yes. Something is that dense. The thing Einstein called a phantom has an address after all, and an edge, and things really can get that small. You're not going to tell me tonight, are you?
Not tonight. Tonight I only wanted you holding all of it at once. The wobble that broke Newton, the starlight that bent by double, the light that climbed up, reddened and tired, all of it pouring out of one exact map a dying soldier posted home from a war. And then, buried in that same map, hidden just beneath all the triumph, this one ring where the numbers scream and everybody agreed to look away. That's the whole of tonight. The map is real. And so, I've come to suspect, is the ghost.
Then I'll carry the ghost up the stairs, right next to Mercury's wobble, and I don't expect I'll get much sleep between the pair of them. It's a strange thing to feel. You've spent the whole night showing me the map that finally got the world right, that took the old broken wobble and the bending starlight and the reddening light and made them all sing the same note, and by rights, I should be walking out of here triumphant. And instead I keep looking at that one ring near the middle, where it all falls apart, the place the very man who built it swore was nothing at all. A radius where the world goes mad, that surely nothing could ever reach, except I've watched you say, surely, one time too many tonight to trust it any longer. So, next time, what's on the far side of that edge? Whether the ghost's got a real address after all, and what it must be like, heaven help whoever finds out, to fall across a ring you can never once climb back out of. I'll be down early, and I'll leave the light on if it's all the same to you. Good night.